Hello and welcome to page 5. This is the final page on the Fall 18 exam. This first problem on part A on page 5 is the same for versions A and B. We have, first of all, the reaction of 2-methylpropene with methanol in the presence of sulfuric acid catalyst, and it gives methyl tert butyl ether. It's a mechanism analogous to acid catalyzed hydration, which we covered to pretty good pretty good extent. And you're asked to write the mechanism, and that implies that you're using curved arrows drawing the reaction intermediates at each step. Okay, so first thing that happens is we do simple acid-base chemistry between these two. And since we're under very acidic conditions, we see that the first thing that happens is that these two react to make protonated methanol and bisulfate, or monobasic sulfate. And this happens, once again, it's an acid-base transformation. So even though this isn't really part of the mechanism, you could have just started with this guy here. Here, let's show one of the OH bonds of sulfuric acid. We're going to have methanol, which is the base, pull off that proton, kick those electrons onto that oxygen. And that's how we get protonated methanol. This is going to be our initial electrophile. So this is going to be a hydrogen electrophile, and the alkene is going to be a carbon nucleophile. And I think before I go any farther, I'm going to make a nice little list of all the bonds that are broken in this process and all the bonds that are formed. Okay. We're not really going to pay attention to the bonds in sulfuric acid itself because sulfuric acid is a catalyst. It's regenerated throughout the course of the reaction. So I'm really just going to focus on what I actually see here, what's actually given in black. And what we should note, let's start one functional group at a time. We have these two carbons. We can identify them as the same two carbons over there. So we can see that we have lost a carbon-carbon pi bond. The other stuff that's different around there is that we have, even more specifically, this CH2 group right there, which is now a CH3 group, which means we must have formed a carbon-hydrogen bond. Okay, we'll go over to the other carbon. We see that we have 3 bonds to carbon, and we have, 4 bonds to carbon totally, but 3 carbons bound. And now we see on the product that we have a new carbon-oxygen bond. New carbon-oxygen bond. And then we skip over to the next reagent, being methanol. We see that that oxygen has 1 hydrogen, and in the product it has no hydrogens. So the other thing that we're going to need to do is break that oxygen-hydrogen bond at some point, which seems kind of funny because it looks like we just formed a new bond, but that's all part of the process being catalytic. We actually have to identify what our electrophile is going to be, which in this case is just methanol with an extra proton. So let's continue with the actual mechanism. We're going to start at the carbon nucleophile, and we're going to end at that hydrogen. Those 2 electrons can get kicked over onto oxygen so that it can go back to having its neutral charge. And our intermediate is one where we have still 3 bonds to carbon, now a new bond between carbon and oxygen. Oxygen still has its methyl group, still has its hydrogen, so it's positively charged. So then we move on. Oops, wow, that was not right. Yeah, all right, well, I'm just gonna keep doing this because I can't edit my videos, so sorry about that. We're gonna draw our product here as actually not having that methoxy group yet. It actually has a carbocation, and you don't need to draw the new hydrogen here, but there it is. We'll take him out. And what we're left with is methanol. Right? Methanol can finally act as an oxygen nucleophile. Over here, this carbocation is going to be a really nice oxygen electrophile. We're going to have oxygen electrons kick over to that carbocation. We're going to get a product that actually now has a new carbon-oxygen bond. Oxygen brings its methyl along with it and the hydrogen. This is, we're almost done. You can add the brackets if you like. We're almost done here. Now, in the second phase of the reaction, or the final phase, we have some base that comes along and picks up that proton. Those electrons get kicked onto oxygen. That base could have been the methanol, in which case, when you're done with this reaction, you just go ahead and regenerate this protonated methanol, which would bring us back to the very beginning of the reaction. And that's how this is a catalytic process. And that's it for part A. Part B has a couple different possibilities in version A and version B. They're different. So right here, again, this is version A. And we will show how to get from this terminal alkyne 1-pentyne into this trans 2-hexene. First thing you may notice is that the starting material has 5 carbons, and this product has 1, 2, 3, 4, 5, 6 carbons. You know exactly one way to make a carbon-carbon bond, and that's by using the acetylate addition that you saw on the previous page. And this is where you go ahead and you pull off this proton using sodium amide in ammonia solvent. You follow that up by adding an alkyl halide with as many new groups as you need, and that is just 1 carbon, just 1 methyl group, and you have to attach it to an electronegative atom so that you actually have a dipole, and this carbon is electropositive, able to pick up those electrons from the acetylate ion. In this step, we have just extended the alkyne 1 carbon, so now we do have our 6 carbons, so check. And then we notice that we're going to be reducing the alkyne, or in other words, we're adding 2 hydrogens and we're adding them trans. This is the 2-step process where we use lithium and ammonia. It's an excess of both. You didn't have to state that, it's implied. But the excess of lithium, or just lithium itself, is going to donate 1 electron to that pi system. And then the protons, the hydrogens, are going to come from ammonia. And this is a 2-step process. Because of that, they have the choice of adding to the more stable, or making the more stable alkene, in this case, which is trans. And that's the multi-step problem for version A. We'll see you on version B.